and we start first with a little announcement on the MIA conference next year in January in Berlin. We hope to see many of you there. Let's go to the webpage, and together with that, there is another announcement that is not yet on the webpage, but will be circulated soon. We are decided to create a PhD prize for French and German PhD students in the field of image or mathematical imaging and signal processing. So if you have good students who have in Germany or France who are submitting their PhD or have submitted them last year, keep an eye on that. There will be a submission soon. Okay, now we start. We start with the talk by Jalal Fadili on sensitivity analysis with degeneracy.
Okay, so thanks very much. I would like to start by thanking the organizer for the nice invitation. Very nice to be here. I did my postdoc here, so I haven't been here since a long time. And Cambridge is a very nice city. I'm very proud to be here again. So this is joint work with Jérôme Malik, who is in Grenoble, and Gabriel Perret, that most of you know, who is right there. Okay, so the starting motivation of this work was about linear inverse problems. Inverse problems in general. I'm just taking the linear inverse problem as a guiding example. So typically you have an object x0, and you don't see this object. What you see basically is a degraded and possibly noisy version of it. Let's call this y, and the x0 has been submitted to the action of an operator here a, and possibly to some noise additive here. And the goal is typically to go from y to get an estimate of x0, and this is typically an inverse problem, and most of the time it's an ill-posed inverse problem, because of the behavior of a, also because of the presence of the noise. Okay, so in fact, most of the time, this problem has been imposed. You cannot recover x0 uniquely. So typically, or even you cannot recover it in a stable way. So, but you have some prior knowledge of the type of object you are looking for. And this prior knowledge that you have typically would be imposed through a regularization or constraint, whatever, on the type of object you want to promote. And intrinsically, what you are using is the fact that x0 lives in some, has some low complexity structure. And this is captured in the fact that x0 will typically live in a low dimensional subset of the whole space. And so this has many, many applications in data science, going from signal image processing to machine learning and statistics. And one of the ways of attacking this problem is through regularization. So typically, you're going to cast your problem as a minimization problem, minimizing the sum of two terms. The first one, which reflects the kind of forward model you have here with data fidelity f, and the other term where you gather everything together. So the regularization, the constraints, et cetera, et cetera. So throughout the talk, I'm going to assume that the function f and the function r are both proper and convex and lower sum continuous, and even f can be will be smooth. Okay. So the class of these functions will be denoted here as gamma 0. Okay. And R is built in such a way that it will promote objects that live in the same. I'm saying here the manifold it should be a set. It's not necessarily a manifold in the same subset as x0. Okay. So what I intend here again, just to recap this, what I intend by low complexity of x0 throughout the talk is the fact that typically the object x0 will belong to some low dimensional subset of the whole space. I'm going to denote it as mx0. So the typical example that most of you know is the case of sparse vectors. So in this case, either you have in R2 or R3, I'm just showing an example here. If you have a zero sparse vector, of course, it has no interest. But in fact, in R2, we're going to promote one sparse vectors, which are aligned with the axis. And in general, this will promote subsets, which are basically subspaces. These subspaces are typically the standard basis restricted to support of the vector x0. Okay. On the other hand, so this is what I'm showing here. So if you take here the zero ball restricted to the alpha ball, and you take the convex hull of this guy, you're going to recover the L1 norm, and this is known as the Tykes convex variation of L0, restricted to the alpha ball. Okay. On the other hand, if you go to the the case of matrices, then in this case you can exactly formulate the same type of prior, but now not on the matrix itself, but on the spectral properties of this matrix. So for instance, if you have a matrix, like call it X again, and if this matrix retrieve its singular values, and if you take the L0 pseudo-norm of the singular values, you're going to get the rank, okay? And here what I'm proposing is in the space of symmetric 2 by 2 matrices on R, I'm presenting here the cone of matrices which have rank 1. So I don't have an fx here, otherwise it would be rank 0. So again, if I do the same trick, I restrict to the Frobenius ball, unit Frobenius ball, you take the convex hull, then you recover this kind of cylinder in this case, and this turns out to be what we call the nuclear norm, which is the L1 norm of the singular values, okay? So in general, what I mean by low complexity, it could be a low complexity either of the object itself or if its spectral properties if it's a matrix. So what I'm going to do here is basically to go back and forth from this kind of regularization to the same kind of regularization on the spectral properties. We call this spectral lifting in the following. Of course, in image processing, we have many other priors. For instance, you can have a sparsity which is not organized individually. It's going to be organized in terms of groups. I'm representing here this in terms of wavelet collections, for instance, of Lena. If you take the squares here, this is the size of your block. You can take L2 norm, you sum all this, then you can have the what we call the group sparsity, or the group lasso, if it's the sum of the L2 norms. Okay, so now if you promote not the sparsity of an object, but the sparsity of the object, which has been taken through a linear operator, let's call it D star here. Okay, for instance, if you take finite differences, and you take, in this case, you have the gradient of your image in each direction. And if you sum just the absolute values of these finite differences, you're going to have an isotropic total variation. If you take the L2 norms of this guy, it's going to be the isotropic total variation in a discrete sense. And it turns out that this is a special case of this guy composed by a linear operator. So you can see also TV as the isotropic TV, sorry, as the composition of the group sparsity with groups of size 2 with a linear operator. But anyway, these are the typical examples that we've seen in many talks previously. Okay. So the questions we are asking ourselves in general when we deal from the mathematical point of view on regularized inverse problems is, again, I'm just putting here, you observe y equal x0 plus epsilon, you solve this problem, and you ask yourself which conditions will ensure that, for instance, you have exact recovery in the noiseless case. It's a sort of consistency, okay? If the noise goes to 0, you want to recover something which is basically exactly x0. The reason is that you put in here a prior that will promote object that will resemble x0, so you want at least that in noiseless case you're going to recover x0, okay? When you put some noise, okay, you want also to have guarantees on how x star will deviate from x0. And you want to ensure that the deviation of x star from x0 for a proper choice of lambda here, you want to ensure that this will behave nicely as a function of the noise, okay? So typically it has some Hölderlin or Lipschitz continuity property, okay? Well, I'm calling this here stable recovery. Okay, the last type of guarantees we're looking for is what we call model stability, meaning that and under which condition you can ensure that x star, which is a function again of y and lambda, will belong to the same model, the low complexity model, as x0. Okay, just to be more precise, think about the L1 norm, okay? If you solve this problem with the L1 norm, you are asking yourself, for instance here, when the solution x star will have the same support as x0, right? Okay, the same number of non-zero entries as x0. Remember that the L1 norm is built in such a way that it will promote sparse objects. For matrices, you're looking for under which conditions you can ensure that the solution of this problem by putting here R as the nuclear norm, under which condition you can ensure that the object that you have here, the matrix that you cover, will have the same rank as the original vector x0 or matrix x0. Okay. And the second type of questions that we are asking ourselves are, what are the algorithmic implications of all this, okay? Because at the end of the day, you formulate your variational problem and then you solve this problem, okay? Then you get some iterates by an algorithm. Let's say an algorithm A that generates iterates xk. These iterates will converge typically to global minimizer to this problem. Assume that the set of minimizers is non-empty. Remember, everything is convex here. So the xk that are here will convert to this x star. And we are asking ourselves, under which condition are we able to prove a property that we call finite activity identification? Meaning what? Meaning under which condition we can ensure that the iterates xk themselves, not x star, but xk itself will belong to the, let's say, the low-dimensional subset associated to x star. Okay? And if you combine the conditions here and the conditions here, you're gonna be able, in fact, to state that in finite time, the iterates here, xk, will belong to the same model subspace as x0. Okay? Just to give an example, imagine that you have here, you're minimizing a quadratic data fidelity, and here you're putting the L1 norm. Okay? This is the Lasso problem. Okay? And if you solve this using, let's say, 4 backward splitting, iterative self-thresholding, if you prefer, then you're asking yourself under which condition you can ensure that xk here would have the same support from a certain number of finite iterations and onward. Okay? For a large number of iterations, you're asking yourself under which condition you can ensure that iterates will have the same support, always the same support. Okay? So these are the type of conditions, the type of questions we wanted to answer. In fact, this is not new. There has been some work on this, and for this to present the conditions that will ensure this kind of properties, just to fix the notations. For a function r which is gamma 0, I'm going to denote here the subdifferential. This is the normal cone associated to a set C. This is the affine Hall of C. This is the parallel subspace associated to C. So this is just R C minus C, and the difference in the Minkowski sense, or the subspace which is parallel to the affine Hall, if you prefer. This is the relative interior, which is the interior but in the topology dictated by the affine Hall. And I'm going to find 2 subspaces which are very, very important. The first one is the subspace which is parallel to the subdifferential, and the second one is the subspace which is orthogonal to it. Okay, these are the only notations I'm going to need. Any questions so far? Okay. Okay, here are the known results. Let's start with the stable recovery. Again, the same problem. Just for the sake of simplicity, I'm going to take the data fidelity as a quadratic data fidelity. Okay. So here are the type of conditions that will ensure you or allow to answer one of the questions that I asked in the beginning, stable recovery. Okay. Assume that typically that the image of A star intersect the relative interior of the subdifferential of R taken at x0. Okay? So if you remove the relative interior here, people in inverse problem call this a range condition, okay, or source condition. So typically what it tells you here is that x0, if you let the noise go to 0 and lambda goes to 0, basically this problem would be minimizing R subject to the constraint y equal to x, okay? If you write the first order optimality condition of this problem, it turns out that the first order optimality condition corresponds to this. Non-empty. So the intersection should be non-empty here. I forgot the non-empty. But here, we're going to take a condition which is a little bit stronger. We're going to take a condition which is a little bit stronger. We're going to require that the intersection should not be on the relative boundary of the subdifferential. Okay? The second condition I'm going to require is, remember, I'm assuming that x0 lives in some low-dimensional subset of the whole space. Okay? Imagine just for a second that this subspace is a subspace. Okay? So typically, I'm looking for the object x0. So because I'm observing this, though A could be non-invertible, if I want to have any hope to recover x0, I must at least be able to ensure that A is invertible on the subspace that promotes x0. Okay? So this is a sort of minimum condition that I have to impose, is that the operator A should be invertible on Tx0. Okay, so if I have these 2 conditions, I'm putting here graphically what it means. In the case of the L1 norm, taking the L1 ball, I'm taking x0 to be here. This is the subdifferential. This is the points are the boundary, the relative boundary. So if you take the parallel space to the subdifferential, it's going to be this axis, and the orthogonal to it is this axis. In fact, for the L1 norm, the subspace takes 0 here is just the standard basis restricted to the support, which makes sense. Okay? And here the condition tells you that if you take A and restrict it to the support of your vector, this matrix should be injected. Okay. So so the first condition that you have here is that if you have the kernel of your operator here A, this is the image of A star, it should intersect the relative interior of the subdifferential, which turns out to be the case here. So basically, we have to avoid touching the relative boundaries. Okay, and at the same time, this condition is fulfilled as well because you can see that the intersection is trivial. So if you have these two conditions, then if you choose lambda in proportion of the noise level for some constant C, then you can ensure that any minimizer x star of this problem will behave in Lipschitz way with respect to x0, meaning that if you see it as a set value with mapping, it is really a Lipschitz application. As a function of what? As a function of the noise. Okay, so x star y lambda minus x0 is equal to, I just wrote it in this way just to see that it has Lipschitz property, x star y0 plus epsilon, lambda is proportional to the noise level, minus x star. So this guy here, if you let lambda go to 0 and the noise go to 0, you can realize that this is x star y0, 0 plus here, which is the solution of this limit problem as lambda goes to 0 and epsilon goes to 0. And this is indeed O epsilon. Okay? I don't give the expression of the constant. It's not the matter here, but we can discuss this offline. So this is a known result. Okay. So now, okay, of course, I didn't say it, but sorry. Okay. Under this condition, we can ensure that basically x0 is the unique minimizer of the noiseless problem. And of course, when the noise here is equal to 0 and lambda goes to 0, you recover indeed that x star is basically nothing but x0, of course. Okay. So now, if we make our problem a little bit more complicated, we ask the question now not to be always stable in L2, here in the norm of your that equips your space. Here, completely Euclidean space, so I'm taking just the L2 norm. But if you ask yourself, I want to have some stable recovery. Okay, think about the L1 norm. If you have L1 norm, and if you have a sparse vector, you're going to observe a degradation of this sparse vector, whatever, compressed sensing problem, deconvolution problem, whatever you want, okay? And you add some noise. If you invert your operator, okay, imagine even if you know the support, okay, you're going to take the pseudo inverse. So what you're going to get is your original vector, x0, if you know exactly the support of x0, plus some noise. Okay, and this noise, okay, that you're going to have is basically the pseudo inverse of the matrix restricted to the support multiplied by the noise epsilon. And this will depend on the conditioning of this matrix. Meaning what? Meaning that basically you're going to have x0 plus some noise. So x0 has some entries which are 0, a lot of entries which are 0, a few of them are non-zero. And you see that basically what you have to do to recover that your estimate has the same support as x0, first, you have to be able to reject all the noise which is outside the support. Okay? Meaning you have to regularize. You have to put lambda sufficiently large. But if you have some entries which are very small, they will be completely overwhelmed by the noise. And you have no hope to recover them. Because if indeed you regularize, you're going to wash them out. Okay? So there is a compromise to have between basically regularization, the choice of lambda, and also of the type or the level of noise that you allow. And more precisely, on the minimal signal to noise ratio between non-zero entries and the noise. Okay? So understand intuitively this is what it means. And this means that you cannot hope for stability or for stable model recovery for any noise, for arbitrary noise. In the previous slide, my noise was completely arbitrary. Here, it cannot be arbitrary. Okay? So the noise will be somehow sufficiently small. Okay? The other thing is that here I'm asking for something which is more complicated than just Lipschitz continuity. And for this, you're going to see that I will have also to make my range condition, which was non-degenerate with the relative interior, okay, to make it a little bit stronger. And now I'm not just assuming that I have a non-empty intersection here. I want this intersection to be a specific vector. Okay? And this specific vector turns out to be what we call the minimal L2 dual certificate. Okay? So everything is related to dual problem. And this dual certificate under this condition in particular can be written in this way with the notations I'm putting here. This is the subspace T and this is the E. For instance, go back to the L1 norm. The E that you have here is just the sign restricted to the support. Okay, so now if this vector is a non-degenerate dual certificate, meaning that its image by A star belongs to the relative interior of the subdifferential, again, you have the same restricted injectivity condition, then in this case, if the noise is not too large, and if lambda is chosen appropriately in proportion of the noise level, as I told you before, then you can ensure that in this case, X star, the solution of this problem, will be unique and will belong to the same model subspace as the same model as X0. Typically in L1 norm, it means that X star will have the same support as X0. Okay, so it turns out that the example I showed before, it turns out that the vector that you have here is precisely U0, is the image of the minimal dual certificate U0 by A star. Okay. Algorithmic implications. Again, if you take this problem, you solve it with the assumption that I had before. You can solve it using the forward backward algorithm. So you have the gradient of your part minus the gradient of your part here. And you have the implicit step here, which is proximity operator of R. If R is L1 norm, this is nothing but self-thresholding. The gamma should be in this interval. And in this case, again, you have theorems that tell you that if R has some nice structure, okay, around X0, the previous theorem was the same thing. This nice structure, I'm going to be a little bit more precise later on it. Okay, again, around X star. And if you have, again, this condition, you see now the condition is almost the same as before, but now you have a different dual vector. Again, this is a different one. Then in this case, for k which is too large, you can ensure that xk will belong to the same model subspace as X star. For instance, again, for the L1 norm, you can ensure for after a finite number of iterations, the iterate will have the same support as the limit point. Okay, we call this finite activity identification. Okay, so now if you take together the first statement and the previous statement on the previous slide, then you can ensure that the same thing holds, but now not for mx star, but for mx0 itself. Meaning if the noise is not too large, then you can ensure that this is even true for the model associated to x0. And for instance, for the L1 norm, as I told you before, is going to be the support of x0. Okay. Okay. So what's the common point between all these slides with these known results? Okay. Non-degeneracy is ubiquitous. What I'm calling non-degeneracy here, sorry, is each time you saw here its condition, you have a relative interior that pops up. Relative interior. Relative interior. You have all the time relative interiority that pops up. Okay? We can ask ourselves what happens if you are in the relative boundary. Okay? Or is this condition easily verified in practice? So this is really the main goal of this work. So non-degeneracy is important. The structure of the regularizer is important as well. And does non-degeneracy hold in practice? The answer, if you take, for instance, the compressed sensing framework scenario, meaning that the A is randomly generated, you can ensure that this condition indeed is verified if the number of measurements is large enough. To be more precise, take the L1 norm and take the matrix A such that its entries are zero mean, they are standard Gaussian entries. And if you take S as the sparsity level of x0, so if the number of measurements is sufficiently large, meaning that it is larger than this bound, then we can ensure that there exists a non-degenerate dual certificate, meaning that the image of A star will intersect the relative interior of the subdifferential of the L1 norm taken at x0. Okay? And this is true with high probability. Okay? Then this is true with high probability. Now, if you want the minimal L2 norm to be a non-degenerate dual certificate, as I told you, this is a stronger assumption, right? And this is exactly what you see here. Look at this. You have, again, 2s log, but instead of having n over s here, you have n, which is larger. And instead of having here just 1, you have t, which is circularly greater than 1. So you need a little bit more measurements to have model recovery, meaning that in this case, Q0 itself will be a non-degenerate dual certificate, minimal L2 norm. So now the question we're asking, what happens if this is not true. Okay? We have answers from stochastic geometry that allow to quantify what we call the phase transition between stability, non-stability, recovery, exact recovery, and non-exact recovery. So we know that this will fail. We cannot have identification of the model, for instance. But can we identify anything else? And this is, again, what was the motivation of this work. So the other thing is that this is most unlikely to be true. The relative interiority assumptions are unlikely to be true for challenging inverse problems, deconvolution, reconstruction in very complicated tomography problems, etc. The operator is so nasty that you cannot ensure that this is true. Okay? So what about these intricate situations? What happened? Can we ensure something? Okay? Can we really ensure anything at all under degeneracy if we don't have this non-degeneracy? And this is what we try to answer in this work. So the answer is yes, if we can afford some structure. Okay? And this structure, you're going to see, this is what we call mirror stratification. Stratification will be very, very important. Okay, so again, just to recap, know the results, assume non-degeneracy and some structure, and we have exact model recovery. Okay? What we're going to prove in this talk is that degeneracy and some structure, you're not going to have exact model recovery, but you're going to have some model recovery. And more precisely, I'm going to give theorems that give you localization of the models that you're going to have. Okay? You're going to have, let's say, the smallest model and the largest model. Okay, so the outline. Let's start with the main notion of this work, which is mirror-stratifiable functions. First of all, I'm going to define a stratification. So if you take a subset D of Rn, and if you take a finite disjoint partition of this set into sets, let's say Mi, for I going from belong to some finite set capital I here, such that the partitioning sets, what we call strata, okay, they fit nicely. What does it mean? It means that if you take M and M prime, which is in M square, then if M intersects the closure of M prime, then it means necessarily that M is in the closure of M prime. Okay, just to give you an example, can you see the gray here, or this is white? It's white or is it gray? I cannot say. It's white? Yeah, it should be gray. Sorry. Anyway, this is the gray. Okay, you can see here, this is a stratification of the unit L infinity ball, for instance. Okay, so you have just the vertices. So this is a very simple example, which is completely polyhedral. You take all the faces, open faces, from dimension 0 to the dimension of your space. So you have the vertices, you have these faces, and you have this one. Of course, the stratification is not unique. For instance, you can take as a stratum this guy, this guy, this guy, and this guy, the union of this guy, this guy, this guy, and this guy, and this guy alone. It could be also valid stratification. Okay, and as you can see here, the stratification is endowed with a natural ordering. And this natural ordering, it tells you the following, is that M is less or equal to M prime if and only if M is in the closure of F prime, which is equivalent by definition to the fact that M intersects the closure of F prime. Okay, so for instance, I'm giving examples here. So M2, for instance, is sandwiched between M1 and M4, and M3 is sandwiched between M1 and M4 as well. Okay? Okay. An operator that will be very, very important throughout the talk is what we call the correspondence operator. So this correspondence operator will play a major role, in fact, to build a connection between the stratification in the primal space and the dual space, as I will show shortly. Okay, so this idea goes back basically to the work of Aris Dimitri Grudevsky, and Adrian Lewis in 2013. So if you take a function R, and this function is proper logarithmic continuous on convex function, then you're going to define the correspondence operator as, so this is a set valued operator. So this operator takes sets in Rn, okay, and then it takes the union of all the relative interior of the subdifferentials for all points that are in this set. I'm going to show examples shortly. Okay, so of course, this is obvious. This operator is increasing for the inclusion, okay? But however, remember, I want to give localization of sets, as I told you. I'm not going to have an exact model recovery, but some model recovery, and more precisely, I'm going to have model localization. And this is the reason why I introduced the ordering that the partial ordering that I have between these strata. And for this operator to have some interest in our case, in particular in sensitivity analysis, I'm going to impose that this operator is decreasing for the partial ordering, which is this one. Okay, and this is exactly what mirror stratification is about. Okay. So I'm going to take a function R, which is mirror-stratifiable. I'm going to say that it is mirror-stratifiable with respect to two stratifications, primal stratification and dual stratification. So it's a primal stratification of what? It's a primal stratification of the domain of the subdifferential. It's not the domain of the function. It's the domain of the subdifferential. Okay? So in this way, I'm sure that the subdifferential is non-empty. Okay? So this is just a technical problem, but if you have a function which has a full domain, it's okay, like the L1 norm, for instance. And a dual stratification of the domain of the Legendre differential conjugate of R, the subdifferential of the Legendre conjugate of this function, which is the inverse, basically, of this subdifferential. If I have two properties, the first property is that the conjugation in the sense of Legendre differential will induce a duality pairing between M and M star, meaning what? Exactly what I was saying, meaning that the operator GR, which is here the correspondence operator, from the M to M star, which are the primal and dual stratifications, is basically invertible. Okay? Meaning that if you have stratification of the primal and of the dual, you can go from one to another in a unique way. Okay, and the second property, just the comment I put it before, here is that this correspondence operator should be decreasing for the relation inferior here for the partial ordering, meaning that if you take two strata, then basically when you say that the stratum M is less or equal to the stratum M prime, this is equivalent to saying that its image by JR here should be greater than the image of M prime by the operator JR. Okay, just to give you, okay, just a small remark. What I'm putting here is for subdifferentials. You can generalize it, for instance, to maximum monotone operators. There is no obstruction. Okay, give you a small example. The same I've been taking from the beginning. If you take R as the L1 norm, the domain of the subdifferential is the whole space. If you take the Legendre differential conjugate of this function, this is the indicator function of the L infinity ball. And the domain of the normal cone of the L infinity ball is the L infinity ball itself. Now, if you take the correspondence operator here and you write it, this is just, I'm writing the definition here, and it's going to be Mi star. And you can verify the simple fact that if you take the domain, again here, there should be a lot of colors. Sorry for that. Okay, so basically the stratification, one of the possible stratifications is having the zero, and then having this half-axis, this open half-axis, this half-axis, and then the quarters of the planes, which are open as well. Okay, this is a valid stratification. Okay, now the image of these guys by this operator are what? Are the stratification that I showed you before of the L infinity ball. Indeed, if you take the L0, the origin here, the subdifferential is what? That is the L infinity ball. I'm going to take just its relative interior, and it gives this guy. Okay, if I take a point here, the L1 norm is completely differentiable. Okay? It means what? It means that the subdifferential is just a point, and this point is a gradient. This is exactly this guy here, etc., etc.
Turn right onto Clarkson Road.
You want to leave? Okay. So because the function that you have here is separable, you can make the reasoning completely simple, just starting from the absolute value. Okay. So now, if you take the absolute value, you define it on R, you can have stratification of the axis in half-axis, and origin, and then you take the Cartesian products of all these guys. It gives you a valid stratification. This is exactly what's in here. Okay. The same thing here. This is completely separable. If you take a stratification of the interval, which is the conjugate of the absolute value, okay, and you take the Cartesian product of all these guys, it gives you this stratification. And in fact, this is what you can see here. -1, -1, 1, open, 1, and just you take the n power of this. Okay. a small exercise to their purpose. Sorry. Okay, just some some examples. We can prove that polyhedral functions in general are mirror-stratifiable. Okay, convex polyhedral functions. So I'm putting here some unit balls that correspond to them. Okay, we can see better now. The L1, L2 norm. So this is the group lasso. As I told you, if you have group sparsity, you take the sum of the L2 norms. You can show that this guy here is, again, mirror-stratifiable with respect to some stratifications. I'm putting here the stratification. So 0 and the whole space except the origin to the power k. K is the number of blocks, and each block has length, which is here b. And the dual stratification are what? Simply, if you take 0, then in the dual is going to be just the sphere. Okay, and the if you take this guy, it's going to be the interior of the ball, and if you take the rest, it's going to be just the boundary of the ball, which is the sphere. Okay, I'm putting again here an example. You're going to check the correspondence between all the points. For instance, the green here becomes this guy and this guy. The red is the interior, which is in here. The orange that you have here, this is this guy, this here, and the gray, which is in fact the half plane, which is above, and the other half plane, union the half plane, which is below, and it gives you this sort of boundary of the cylinder. Okay, so of course the strata are not convex. Okay, so the last example is the nuclear norm. So this is again just the nuclear ball, and in this case the stratification corresponds to the sets in the primal. This is the set of constant rank matrices. So mi, I is an integer. They go from 0 to the rank, for instance, with dimension if you prefer. This is the set of matrices that have rank I, and this is known to be a Riemannian manifold. So it turns out that in these cases the strata are manifolds, but this is not necessarily so. Okay, we don't need this at all. We don't need smoothness. Okay, this class of function is quite nice. It enjoys a nice calculus. So for instance, it is separable. So if you have a function which is separable, if you know the stratification of each function, you just take the Cartesian product of the stratification. It gives you a stratification of the whole function. It has a very nice property as well. This is what we call spectral lifting. For instance, we know that the L1 norm is stratifiable because it's a polyhedral function, mirror-stratifiable. And because the nuclear norm is nothing but the L1 norm of the singular values, and because of this property, you know that the nuclear norm is mirror-stratifiable as well. Okay, so if you know that the function is mirror-stratifiable, if you take spectral lifting of this function, then it is mirror-stratifiable as well. So this is just the technical statement of this. However, there is a problem. There is a problem because this is not stable to sum. And the reason is quite simple. The reason is quite simple is that imagine that you take a function, which is the L1 norm, and you add to it a quadratic term. When you go to the dual, you're going to get the mirror envelope of this guy. Okay? It's an infinite convolution, so it's the mirror envelope of this guy. The mirror envelope has a gradient which is Lipschitz, so it's differentiable everywhere. And the thing is that you don't know how to, you know how to stratify this function. It's the whole space. Okay? So though this function is completely non-smooth, this function is going to be smooth. And this is because of conjugacy. Conjugacy is a duality between strict convexity and smoothness. Okay? And because of this, the sum rule cannot be true. Okay? Meaning that you cannot go just by summing functions. If they are mirror-stratifiable, sum will be mirror-stratifiable. This is not true. Okay? So I'm giving, again, this example here. Okay. So a lot of examples that I gave you are mirror-stratifiable. I gave you the polyhedral functions, the L1, L2, the nuclear norm. Their image, if you take the image by linear operator of these guys, so they remain mirror-stratifiable. And again, I'm insisting on the fact that we do not need that the strata are manifolds, which is in great difference with respect to existing results, even the ones that I showed before when I said nice behavior of the function near the point. Remaining geometry is always in there. And there are a lot of functions which are mirror-stratifiable. For instance, polyhedral functions, semi-algebraic functions, in general tan functions, where we know that from omnimal geometry and semi-algebraic geometry that they admit stratifications, and we call this weakness stratifications, and it turns out that the stratifications in this case are even manifolds. Okay, just a few results on sensitivity analysis and the application of this. For the first question I asked, mean instability and sensitivity analysis. Okay, let's consider this problem. This is a parametric convex composite problem, smooth plus non-smooth objective function. So the E here is a function of x and p. P are the parameters, which belong to an open subset of finite dimensional linear space. And x is my variable of interest. And E is f plus r. So the f is, as before, think about it as data fidelity. It's not the case here, but anyway. And r here is, let's say, your regularization. Okay? So what sensitivity analysis is about the properties of the minimizer of this problem, let's call it x star p, to a perturbation of the parameters p around some reference point p0. Okay? Which is exactly the abstract way of putting of asking our question, what are the stability of my inverse problem if I solve it through a variational formulation. Most of the existing results on sensitivity analysis, they require non-degeneracy, meaning that minus the gradient, smooth part here, should belong to the relative interior of this Sept differential. Okay? Here are our first results. If we have some mild conditions on the function E, so well-posedness, some continuity, and some compactness, of course. Okay? Then, in this case, if R is mirror-stratifiable with respect to primal and dual stratifications here, then if you take P sufficiently close from P0, if P varies around P0, then any minimizer x star P will obey this model localization. Look at this. Mx star P will be sandwiched between two strata. The first one is Mx star P0, the reference point P0. Okay? And remember, I said that x star P0 is the unique minimizer of this guy, so this guy is unique. And this stratum, which is here, which is the image of the correspondence operator of R star. Just remember, this is also the inverse of the correspondence operator of R. M star U star P0, and this guy here is minus the grad, just minus the grad. This is a dual vector, if you prefer. So basically, what it tells you, the theorem, is that for P around P0, what you're going to get is a model of your minimizer, which will be sandwiched between two strata, the one of the original vector, x star associated to P0, and one which is larger. Okay? So in the no literature, if your function has some nice structure, typically what we call partial smoothness, so you need, for instance, that your function behaves smoothly along some manifold, blah, 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 blah. And if you have this condition, which is a non-degeneracy condition, what you can ensure in this case is that the inequalities here become equalities. Okay, just show you an example, a projection, a simple projection. This has nothing to do with uniqueness, by the way. Okay, so here, just simple projection. We know that minimizer is unique. So I'm writing here this as the first order minimality condition, which responds basically to the monotone occlusion. This is the normal cone associated to the infinity ball. You have the dual problem, which is here basically self-thresholding. Okay, so now I'm going to take the non-degenerate case, meaning that U star belongs to the relative interior of the normal cone taken in x star P0. Take P0 here, its projection is this point. This is the normal cone, so right here. Okay, this vector that you see here, I'm putting here, I'm putting it here. Remember, by definition, this is P minus x star P. So this is U star P0. And you see here that U star P0 is indeed in the relative interior of the norm cone of the infinity norm, as at the point x star P0. Okay? So in this case, if you perturb P0, so for any point around P0 here, for instance, P, you see you're going to stay exactly in the same here stratum, which means here this quarter plane which is open. Okay, so this one I'm putting here. You have equality of all identified strata. So now, if you are in the relative boundary, this is exactly what I'm putting here. Again, you see the problem is that in this case, when you project here at this point, if you perturb around this point, if you are here, you're going to project here. If you are here, you're going to project here. Okay, so you're going to have two models. However, the dual vector will always live here, which is the largest one. And if you put it back, it's going to give you M2 here. Okay, meaning that depending on the perturbation, either you identify the model which is associated to x star p0, or the one which is slightly larger. And this one is indeed the pre-image by JR of the manifold associated to the dual vector u star p0. Okay? So just for a simple projection problem, you see that you have instability if you are on the latent boundary. Okay, this is what's predicted by the theorem. Okay, so now you apply this to regularize inverse problems. You may say, oh, I'm going to apply the previous results. No, you cannot. And the reason is quite simple, because I required some continuity assumptions previously, especially as a function of the parameters. And it turns out that here, if you let lambda go to 0, you lose continuity. Okay, you're merely lower sum continuous, but you're not continuous. So you cannot apply the previous results. Here, the results is more involved. Okay? Again, so now this vector will play again an important role. So this is the one that we know. Again, just recall, this is the known result. And you have equality here of the models. Now, in our setting, again, the minimal L2 norm certificate will be important, as before. But exactly in the same regime, if we have mirror stratification, what I can assure you, if we don't have degeneracy, the model that will be identified will not be that of x0, but will be sandwiched between that of x0 and the pre-image of the one associated to a star q0, where q0 is the minimal L2 norm certificate. Basically, what it tells you in the case of the L1 norm, it tells you the following. It tells you that what is going to happen is that you're not going to identify this support. You're going to identify something which is between this support and a small extension of the support. You can have extra spikes that pop up. Okay? So the analysis, for instance, for deconvolution has been done by Gabriel and Vincent Duval for the deconvolution problem in the continuous case. And you can predict exactly where the extra spikes pop up. But in general, this is an open question. Okay, algorithmic applications of this. Again, you take your problem here. You suppose that F and R are both in class gamma 0, and F is C11 with 1 over beta Lipschitz gradient, and the set of minimizers is non-empty. You apply the forward backward algorithm. This is the known result. Okay, it tells you that for k which is large, mxk will be equal to mx star. What our result will tell you is that if you have mirror stratification, mxk will be between mx star and some larger manifold, exactly as previously. Okay, and this is what we're going to see in the experimental results as well. Okay, so I'm going to go fast on this, but what I showed here for backward, you can do it for any algorithm you want. This is the largest class of, let's say, proximal splitting algorithms that can solve this kind of complicated problems. This is the nth convolution, this is an addition, blah, 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 blah. And primal dual splitting applied to this, you can also analyze it through this point of view. And if you apply this algorithm, for instance, this is not the other one, but it's one of them, but it doesn't change anything in our results. Then basically what it tells you is that the primal iterate will be sandwiched between two strata, and the dual iterate will be sandwiched also between two strata in finite time. Okay? And this has algorithmic applications that people see. They see that somehow the iterates after a finite number of iterations, there, for instance, if you have the L1 norm, their support will stabilize. Okay, just a few numerical results. Here I'm going to take the compressed sensing scenario in the least favorable regime, meaning that the number of measurements is not large enough. I'm taking it for the L1 norm and for the Nicolain norm, but the results are the same. I'm solving this problem and also this problem to get the dual certificate to be able to compute this guy here. The dimension of the largest manifold minus the dimension of the smallest, stratum minus the dimension of the smallest stratum. And this is what we call the excess index, the complexity excess index. Okay. We generated 1,000 realizations of A, noise, and x0, okay, completely randomly. And we counted the number of, this is a histogram of delta. So what is delta? This is what I'm putting here. This is just the complexity index of x star minus x0. It means what? We counted the number of times where the solution had the same cardinality of support as the original vector, and also here for Nickel norm, just the difference of the ranks. Okay, you see that you have here something which is increases and then decreases, meaning that most of the time you don't have exact model recovery. This is what it means. Okay, meaning here 0 is exact model recovery. Most of the time you have an excess. Okay, which is around 5 here, meaning that what you identify is larger, has a support which is larger than the original vector x0. Same thing here. Okay, you have an excess of 2 with respect to the rank, with respect to the vector x0, which means that this is exactly what you observe in practice. We don't have exact model identification in the least favorable regime of compressed sensing, even if compressed sensing, if the number of measurements is not sufficient. This is what we call enlarged recovery. It means that we are identifying a larger stratum. So in general, we don't have exact recovery. So now, what we did in this experiment, exactly based on the experimental setting I explained in compressed sensing, we are counting the proportion of vectors x0 that are the unique solution of the noiseless vector, such that the complexity excess index is less or equal to delta. Okay, so just I'm recalling this complexity index here. So remember, this is the largest one, this is the smallest one, predicted by the theorem, and we're just quantifying the difference between the two. Okay, let me guide throughout this, don't read it. When we have a blue curve, it means that we have stable exact recovery. And we have a phase transition, as you know, in compressed sensing, meaning that until this sparsity level, for instance, you have exact recovery. And then as the sparsity increases, the probability of exact recovery decreases. But what you can see, if you allow now some error on the model recovery, then you can have higher probability of recovery. This is what we see as we move from blue to red. However, the model which is recovered is unstable. We know this. This was predicted by the theorem. And you have the same thing for the nuclear norm if you count this in terms of the rank. So the conclusion of this is that this phase transition phenomenon, they reveal a typical trade-off that you have between the complexity of the input vector, okay, and also of the stability of the stratum that you want to recover in presence of noise, even small. Okay, so you have to have some kind of a trade-off between the two. And you have also, in terms of algorithms, if you apply the four backward algorithm, for instance, to the problem that I showed before, what you have here is that this is an instance where you have exact recovery, you see. Now, in this case, the original vector has sparsity of 10, and after a finite number of iteration, indeed, the x case has exactly sparsity of 10, as I showed you, okay? But now, if you have instability, it means that now you allow an excess of 10, then now what you identify is a stratum. It turns out that this is a subspace who has a dimension which is larger, and it turns out that in this case it's 10 plus 10, which is making 20. Okay? However, you have to be careful because what our theorem predicted is that we should be somewhere between the two. We have never predicted that what we identify is exactly this one. And this is what we observe in practice. Okay? This is an open problem. And the same thing for the rank. Okay. So I tried here to convince you that there is some hope to have some analysis of the theoretical guarantees of inverse problems beyond non-degeneracy. But in this case, you have to sacrifice the exact recovery to some notion of enlarged recovery, either for inverse problems, but also for proximal splitting algorithms. So the analysis can be generalized to maximum monotone operators. So you can think, for instance, about if you have a saddle point problem, and beyond, of course. So what I show you in the experiments is that most of the time what happens is that we identify the largest manifold, but this is not what's predicted by our theory. One of the papers that I know is the one by Gabriel and Vincent, who is able to do this exactly for the convolutional problem, where we indeed have identification of what we call the extended support, and we have a sharp analysis of exactly the spikes that pop up. But here in full generality, we don't have such a result. Okay, how to go to beyond convexity? For instance, everything is based on duality here. Doesn't make sense beyond convexity. There is some hope for some structured problems, and also to go beyond finite dimension. So the papers are on our web pages, and thanks very much.
Maybe we have time for one short question, if there's urgent questions. Otherwise, we postpone to a coffee break.
No problem.
And on with the next talk. Thanks a lot.
Thanks.